command vertex, create coordinate 0, 5.8, create vertex, vertex 2, okay, then 0, 100, that is for domain. That point you cannot see because it is outside the screen now, we will see later. And then I have to draw the nozzle. So this point, since this point is the domain starting, we will draw the nozzle to the left side, so it will come as minus, okay. So that will be minus, the length of the nozzle is 35.5, so minus 35.5 comma 0 is the length of the nozzle, okay. So this is, you can see the length of the nozzle. Then same at minus 35.5, you will plot another point for the diameter of the nozzle, 15.2, okay. So you have drawn the nozzle now. So you have drawn the domain, and we will plot the domain points. So 400, domain size, domain length is 400, 400 comma 100, 400 comma 0, and 400 comma 5.8. So you can see the full nozzle and the domains. Now I am going to connect all the vertices using lines. In Gambit we call it as edge, okay. Line is called as edge. You can see this is the edge button in the second button in the geometry. Go to edge command button, then create straight edge, okay, creates a real or virtual edge. So I have to connect the points. So the trick is, this is some trick. So please start from left to right, left to right. You click with left click using the diamond pointer. So left point to right point. So 2 points you select, and then you right click outside, you will get a line. That yellow color line you can see. So this is one. Similarly, you start from top to bottom, okay, top to bottom, then left to right, again one more line, top to bottom, one more line, then left to right, again from here. So I have created a closed nozzle with the domain, and please remember, don't connect this, okay. This is not necessary, you need not connect this, because from nozzle I am getting a free flow, so I need not connect this 2 points. It's a single entity, okay. Then after the edge, I have to make this as a surface. So first we have created the vertex or point, then we have connected with lines or edges. Now we have to make it as a face, that is surface. So go to surface command button, face command button opens a subpad related to operations involving faces. Now I am going to make all these edges as a surface. So you want to select all the edges, pick all the edges, and then you right click. You will see the color change. Previously it was in yellow color, now it will be in some green, okay. Now you have created a face, so wireframe is over, okay. Geometry you have done. Now you have to do the mesh. So geometry command button, next to geometry command button, you will have the, in the operation in the top, you will have the mesh command button, opens toolpads that allow you to create and modify the mesh. In that mesh, first one will be the boundary layer mesh. Boundary layer mesh is not necessary in high speed jet flows, that too for subsonic flows, but if necessary you can keep in the top layer of the nozzle for some layers, but some small Mach numbers it is not necessary, but anyway we will create a small boundary layer Okay, so if necessary we will create it, then we will go to the uh, edge mesh. So what we will do, so I am giving a small trick to make the near field as a fine mesh and far field as a coarse mesh. Okay, so I will tell the values, so you can follow the values. Those who are using Gambit, those who are using other softwares also, you can follow the same values. First I'll mesh the domain. You click this domain length, domain bottom line and top line. So you put interval size as 4, ratio as 1.025, and you come here and right click. So your meshes have been created, edge mesh has been created. Similarly, you select the vertical lines of the domain. Again you make it the interval size as 4, and then success ratio you give something around 0.89. Then you close this. Now one more thing you have to give, like this and this will be different counts. That count should be same. It is 15 here. Now you can make it as some 10, and then you can give this. Similarly, this count and this count should be same. You can make it. So close this and then go to face command button. Click on face command button. So it is already a face. So you select the face. So you can see the color change. The face has been selected. Nothing you do, just click right click. You will see the mesh, which means you have a closer mesh. If you zoom this, you will see the closer mesh in the, you see closer mesh in the near field, and in the far field it is very fine, very coarse. Okay, now I have to do the boundary conditions. So go to the zones command button, which opens a toolpad that allows you to specify boundary and continuum shapes. Now in that, specify the boundary types command button. Then now defaultly it will be in wall. So select the nozzle top will be wall, and this domain left hand wall will be wall. So you assign this as wall. Go and right click it. Right click it. It will be named as wall. Then the inlet will be a pressure inlet. This is the nozzle inlet. It will be a pressure inlet, and the symmetry, for symmetry we are making this nozzle axis and domain axis as wall, sorry, axis. Okay, so this will be axis. Then other things will be outlet. This one, and this one will be outlet. That's all. Now this is boundary type. Then continuum type. You mark all the flow in this as a fluid. Okay, so fluid is there. Now file, save the file, save as. You give some this is single jet. So you give the author name for credit, Lovaraju. Dr. Lovaraju is the author of the paper. You give Lovaraju single jet. So he is the author of the paper. You give credits to him. So Lovaraju single jet, you give accept. So you can see on the top it have been change it to lower Raju single jet. So in transcript you can see command save name lower Raju single jet. Now export this file as a mesh file. Click on 2D and then you give accept. You can see in transcript it will show export fluent lower Raju single jet .msh mesh was successfully returned to lower Raju single jet .msh. So it is all done. Now again if you want you can save it, then file exit. Again it will ask to save, give yes, this window will close. Now you go to Fluent, so you select in dimension 2D, processing option serial, whatever folder you want you give, you click OK, Fluent will open. You enable the graphics window, enable toolbars, enable tree. This is Fluent 16. You can also use an extended version of Fluent. So file read, we are going to read the mesh. So file read mesh, my file is in desktop, Gambit for students, lower Raju single jet, OK. So it will give you a warning, don't mind the warning, I will tell you what to do. So but the mesh is not been displayed here, so you go to display, you give display. Now you can see the mesh which we have created. So slowly you see how to change the solver type. So solver type is density based solver because we are dealing with compressible fluid flow. Then it's a steady flow and it's an axisymmetric flow. That's why the warning is given. So you change the type 2D space as axisymmetric. And it's important to scale because you don't know in what dimension you have created the mesh. You go to scale mesh, you give mm, mesh was created in mm. Yes, I'll scale back. No, close it. Click again scale. Mesh was created in meter, we'll put. Mesh was created in mm. Unscale or scale. This is correct. This is correct. If you view the length in mm, now it will come correctly. 35.5, 400, 100, 0. So now we have scaled. Okay. You close this dialog box. Go to models. Turn on the energy because I have to solve energy equation also. But defaultly it will come continuity momentum. Okay. Then you can choose any viscous model. This is not laminar flow, this is turbulent flow. You can choose any model. I am choosing some k omega model. Arbitrarily I am choosing. You have to do a turbulence model study. I am choosing k omega BSF because I know the model is giving some better results than other models. So click OK. Go to materials. By default it will be air. It will display 1.225. You change that to ideal gas. You give change create and then close it. Go to boundary condition. You have to set the boundary condition. Pressure inlet. The gauge total pressure is in Pascal, so I have to change the units here. So go to define units, get the pressure units. It is in Pascal, change it to atmosphere. Close. Again click pressure inlet. Your gauge pressure. So you remember I am going to give gauge pressure. So in our earlier class you have seen the pressure converted to Mach number. So I am going to give the gauge pressure. So if it is for Mach 1 sonic Mach number, so I have given 0.89. Okay. We will do for a subsonic case, maybe for 0.6 Mach, so we will give 0.2755. One is the So we are giving gauge pressure. If we add 1, it will become an absolute pressure. So click OK. Solution methods, need not change anything. Go to solution control. Current number will be 5. So this is an important parameter. Now I think you need not change this number, but for supersonic flows, boundary condition is enough. We have set the boundary condition. So current number will play later. Now I think it is not necessary to play with current number. Solution initialization, go to standard, compute from pressure inlet. You can see the velocity inlet 201, it is around 0.6 Mach. So you click initialize, then go to run calculation, give some number of iteration, maybe some 1000 iteration you give. Click the calculate button, your iteration will start running. The convergence time for this is very simple. This is very easy mesh. Very number of mesh is very small. So the computational time also will be very small. It will converge within a minute. So this is an effort of 3 years to find this mesh refinement. I have taken 3 years in my life. Okay. So calculation is complete now. So click OK. So we have done the pre-processing. Processing is over. Now we have to do some post-processing. So first you file, write case and data. You give Mach 0.6, M 0.6 and then click OK. Fine. Now you go to graphics window, go to contours if you want to see some contours. You click on velocity. You first click compute, you will get the velocity, maximum velocity 200.1. You have displayed, but it is not showing here. Again you click, you select filled, display again. So only half is displaying. You go to views, click on axis mirror planes, apply, you will get it. You can see this is the velocity contour. You can see on the morning I have told you, see in the nozzle, it is starting with some low velocity, it is accelerating to high velocity. You can see that red color is 200. That red color core is coming to some distance, that is called potential core. Then that green color is, you can see my mouse pointer, that green color is the characteristic decay, and then it becomes fully developed. And you can see there are some issues here. This is because the error can still be converged. So what I do, I will run it again for the sake of getting a better convergence. So go to monitors, click on residuals. You increase this criteria. It is 10 power minus 3 now. So I am increasing to 10 power minus 6. Click OK. I am just clicking on continuity only. Run the calculation again. So you can see what are the residuals are converging. In the x-axis you will see the iteration, number of iteration, y-axis is the error. So previously we have kept 10 power minus 3 as the residuals. Now we have made the continuity equation alone, this white color line alone, to get into 10 power minus 6 I think. So you will wait for the convergence. You can see continuity is converging, x velocity is converging, y velocity is converging, energy is converging. We have selected k omega model. So k is converging. K is called turbulent kinetic energy. Omega is turbulent dissipation. Okay. So I told you if you want faster convergence, you can play with the Courant number. But as of now itself, the Courant number is very high. This will converge only for subsonic flows. If you want to high quadrant number, you can go for very coarse grid. If you make the grids even fine, now it has been converged. Now you can see the okay. We'll wait for convergence. It will converge. I know my grid will converge. But even then, that is not an issue. See, converged. So I have a 100% confidence on my grid. My grid will not cheat me. Now, if you see the contours, that trailing edge patches may have disappeared. You see, if you make it filled. Yeah, now you can see a better view. You can see a better view. Now see that the trailing edge patches have been gone. So you have a complete flow field now. Now again I will tell you the nozzle, the purpose of the nozzle is to reduce the static pressure and increase the velocity. Now I am showing you the velocity contour only. So it starts from some low velocity to red color 200 meter per second. That red color region shows you the potential core. Then the green color is the characteristic decay region, and then the fully developed region. So if you see the plots, if you just see the plots, if you want to see the velocity plot, go to axial velocity plot. You see, can clearly see velocity has started from nowhere, something around 20 meter per second. It has been raised in the nozzle to 200 meter per second. That is because that is the function of the nozzle. Okay. So in 35 mm length itself, it has 20 has become 200. That is the idea. This is called as the potential core, which I have taught you in the morning. This is the characteristic decay. So here you can, the slope is getting decreased. So this is called a fully developed. So these are the three regions of the jet, and our aim is to reduce this potential core length. That is our aim. So now I will do some small post processing work. So you write this to file, go and write, select the same folder. So center line CL, we'll write the Mach number instead of velocity. If you have Mach number, first plot the Mach number and see. You can write this to a file, go to desktop, Gambit for students, CL Mach number, MN, okay, Mach 0.6, okay. So you click on OK, the file would have been written, see close, open an Excel file arbitrarily, go to open, desktop, Gambit for students. Initially Excel file, no file will be there. You click on all files, you click on this, you give next, click finish. So there is an error, it has not been written. I think there is an error. Again you write the file, again showing error. I don't know why it is showing the error. We'll embed graphics window and we will try again. Write again showing error. We don't know. Maybe. Pardon? Okay, we'll save it again. Write case and data. We'll plot it, write it. Change the file name. File of type. Oh, that is XML file only. Maybe file name is problem. Mach The dot may be a problem. I think now it will come. Again open it. US.
Right extension.
You come. See, this is the data. You can plot this data. Just plot this. So data or view or insert scatter. You can see this is the Mach number plot. Okay. So you can see potential core here. I have to non-dimensionalize it. Both. So this is x and this is Mach number. So I will non-dimensionalize with x by d. D is the diameter of the nozzle. So diameter of the nozzle is what? Exit diameter of the nozzle. Diameter of the 11.6. That is inlet diameter. I am talking about exit diameter. Nozzle. That is exit diameter. We'll talk about exit diameter. Exit diameter of the nozzle is 11.6 mm, which means 0.0116 meter. So you divide this by 0.0116. Similarly, you divide this by exit Mach number. This divided by 0.6. So we will plot from here. Insert, scatter. Yes. You can see we make this as some 2 decimal. Now it is fine. You can get the potential core length here. This is the length of the potential core, or you can go up to 5.99. So 5.8 is the potential core length. Okay. So all these things you can get. You can go to the paper and see the potential core length of the single jet. It's around 5 only. See, without co-flow. Without co-flow means single jet that we have done. See, this is around 5 only, right? Sorry, this is without co-flow. So green color line is around 5. They would have mentioned in the text also. See, you can see potential core of the no co-flow, potential core of the up to x by d equal to 5. So around x by d 5 we are getting. Okay. So even more you can try with some other turbulence model and we can make it even more better. So this is the post processing. You can save this file. This is not saved in as an Excel file. You can save this as an Excel file. Okay. So that comes to the end of the subsonic flow problem. This is single jet problem. In the next class we will try for a supersonic jet problem. Okay. And any doubts you can ask me. Okay. You can ask me. Okay. Thank you.